comma, the air inside expanded slightly. However, the water in B formed steam, comma, which forced out the air. Period. When they were cooled with the caps on, the air in A contracted slightly, creating 13 pounds per square inch, PPSI. The steam in B turned back into liquid water, leaving a vacuum, with 0 pounds per square inch. Okay, now that's all I'm going to write. I'll read that over in case you can't read my writing. Because B contained water, but A didn't. When both were heated, the air inside expanded slightly. However, the water in B, I forgot the B here. The water in B formed steam, which forced out the air. When they were cooled with the caps on, the air in A contracted.
Mrs. Ricketts,
Yes.
can we see Donald Connolly, please?
Okay.
You.
The air in A contracted slightly, creating 13 pounds per square inch. That's not very clear there. The steam in B turned back into liquid water, leaving a vacuum with 0 pounds per square inch. Now, if you read that and you saw what happened here, you should be able to understand that it's the difference in pressure here that caused that can collapse. I present this every year to about 400 to 500 fifth graders. A lot of them have seen this demonstrated at the Pacific Science Center or on TV, but almost everybody comes away with the wrong idea about why they can't collapse. Almost everybody I've talked to thinks it's because the steam sucks in the sides of the can. No, the steam doesn't suck in the sides. The steam turns back into liquid water, leaving a vacuum here with 0 pounds per square inch. Okay, now copy that. And then I'm going to erase this because I want to explain to you why there are 14 pounds per square inch of air at sea level. I'll leave that up there so you can copy that later on if you need time. I'll put these down so that they don't obscure your view of the board. All right. give you, how many of you have that already copied? Does anybody have that copied already? A few of you do. A few of you do, okay. All right. Okay, I'm gonna draw a diagram. Suppose this is the Earth. The Earth is 8,000 miles across. If you draw a line through the center, 8,000 miles. The Earth is surrounded by the atmosphere, the air. But it's only 63 miles deep. So obviously I haven't drawn that to scale or proportion, because if I do that to proportion, this is 8,000, 63 miles would just be a green line right next to the black line. But I drew it larger than that because I want to illustrate a point. If you take a column of air 63 miles high, that big around, it weighs 14 pounds down here at the bottom. That much air weighs 14 pounds. And up here it weighs 0 pounds, for the same reason that if you put the bathroom scale on your head, it reads 0 because there's nothing pushing on it. See, up here there's nothing pushing. Now, as you go higher in elevation, the air pressure gets lower. 14, 13, 12, 10, 9, and so forth. Out here where the astronauts work, the air pressure is 0, it's a vacuum. So that makes their work very dangerous, because we live best in 14 pounds per square inch. We can't live at all at 0 pounds per square inch. So what do they do in order to exist out there? What do you notice about the astronauts when they're on their spacewalk? What do you notice about them, Jackie? They have these very thick suits that have pumps in them to keep the air pressure inside the suit at 14 pounds per square inch. Okay. Now, if we feel most comfortable in 14. If you go up to Paradise on Mount Rainier, how many of you have ever been up to Paradise? A lot of you should have been because you live close to there. Okay, the elevation of Paradise is about 5,000 feet. So the pressure up there is only about 12. If you went immediately from 14 to 12, you wouldn't feel well. But usually you drive up, and on the way up, your body adjusts as you go up higher in elevation. What? Yeah, and I'm going to explain why your ears pop. Right. Okay, now, up here where the jet planes fly, they cruise at about 35,000 feet when they're going from continent to continent, like from here to Japan, for example. Okay. The air pressure up there is only about 7. But we can't exist in 7. So what do we do to make sure we can ride comfortably in the airplane? Does anybody know, Jonathan?
Is there an oxygen mask?
No, it's not the oxygen mask. They're in case of an accident. You know what's done, Allie, to make us feel comfortable in a jet cruising at high altitude? No. Raise your hand if you've ever heard the term pressurized cabin. Ever heard that term? If you get on a plane at SeaTac Airport, the doors are open when you get on. It's 14 on the outside and 14 on the inside. Then they close the doors and they take off and they begin climbing. If they're going to another continent, they go up to 35,000 feet and eventually get up there where it's only 7. Well, as they climb, there are pumps that keep the air pressure at 14 on the inside. That's called a pressurized cabin. So you feel okay. Now, here's something important to know. If an object like a bullet or a rocket made a hole all the way through the side of the plane, the pressure would suddenly go from 14 on the inside to 7. And everybody would die instantly from the sudden depressurization. Okay, that's important to know. Now, I'm going to tell you a couple of stories that are related to that. About the year 2001, I think it was, there was a man named Richard Reed who got on a plane in England. The plane was flying to New York, and when they got up to cruising altitude, somebody noticed that he had a fuse like a firecracker fuse sticking out of the side of his shoe, and he was trying to light it with a cigarette lighter. Well, they tackled him and took the cigarette lighter away and took his shoe off, and they found out that the heel was hollowed out and there were plastic explosives like the terrorists use inside. He was trying to cause a big explosion. Well, he didn't have enough plastic explosives to blow up the plane. He did have enough to make a hole in the side of the plane, and that would have killed everybody anyway, because the plane would have suddenly depressurized down to 7, and everybody would have died instantly from that. He's now in jail. He was a terrorist. One of the real dangers of terrorists is they don't care whether they die. Their main goal is to kill other people, and they don't care whether they die along with the other people. So that makes them very dangerous. People who don't want to die aren't nearly as dangerous. Okay, now here's another story. I want to tell another story. About 10 years ago, there was a famous golfer named Payne Stewart. He was very recognizable because he wore sort of a flat cap and he wore puffy sweaters and knickers, knee-deep pants. He was very colorful. He played in a lot of golf tournaments all over the world. Well, this one day he had a tournament in Florida, and he had his own private plane and his own pilot, and it was a pressurized plane. He finished the tournament in Florida, and they headed for Texas, where the tournament was going to be the next day. Well, they didn't get to Texas. The plane ended up crashing 2,000 miles off course up in South Dakota. Well, it crashed in a field, so they were able to examine the wreckage carefully, and they found that one of the windows had popped out. See, when they got up there at 35,000 feet, the pressure on the inside was 14, but on the outside it was 7. Those windows in airplanes have to be built very strongly to withstand that kind of pressure difference. Well, the window blew out, so they died instantly, but the plane was on automatic pilot and it had a full fuel tank, so it flew up to South Dakota before it ran out of fuel. But, did you know?
How does it make it pressurized in it? Like,
There are pumps that keep the pressure up inside the cabin. Okay, now, here's another thing to know. I'm going to draw a picture of a student here. You might recognize him.
that's Tanner.
Okay, he's got big ears.
That's Educator. You've drawn the student before. That was Educator.
Okay, now, there are 3 parts to the ear. This is just a diagram. There's the inner ear, the middle ear, and the outer ear. And if you look in the outer ear, the doctor looks in the outer ear, he sees your eardrum. That orange structure is the eardrum. And then there's the middle ear and there's the inner ear. Well, the inner ear has a nerve that goes up to the brain, and it's impulses through that nerve that allow you to hear. If that nerve gets damaged, you may have heard the term nerve damage when people are deaf, okay? But the middle ear is connected to the throat by this tube called the eustachian tube. In the back of your throat, there are 2 openings back there, and if a doctor thinks you've got an ear infection, he'll not only look in your ears, but he'll look in the back of your throat, and if those openings are inflamed, he knows that you've got an ear infection. Okay, now I'm going to draw an enlarged drawing of that ear, like this. Okay.
That's how it's his ear.
All right, there's the inner ear with the nerve leading up to the brain. Here's the eardrum. Oops, I drew the wrong color. The eardrum is supposed to be orange, okay? There's the eardrum. All right, and then of course there's the eustachian tube leading down to the throat, like this. And that's covered by a flap of skin down here. Normally that's closed. It opens up if you open your mouth very wide. Okay. Now, down here,
That felt weird.
the pressure out here is 14. And right now, the pressure in here in your ear should be 14 too.
When it's 50.
This eardrum, it vibrates, and that's what allows you to hear. The vibration of the eardrum allows you to hear. It can only vibrate if it's relaxed though. Okay. If you drive up to Paradise, you get up there, and the pressure is only 12.
It makes me very uncomfortable
Well,
when I drive.
in that case,
Like,
the eardrum bows out like that, and it's very tight and you don't hear as well, and you don't feel comfortable until you open your mouth wide, and you hear your ears pop. Your ears popping really is the eardrum snapping back into the relaxed position. That's what your ears popping is. Okay, so you get up there, you open your mouth wide, maybe on the way up you do it a couple of times and you hear your ears pop every time. You get up there, and then the pressure is 12 because when you open your mouth wide, that allows this to equalize. So then you hear okay. But then you come back down, and you get back down here, and the pressure is 14 now on the outside, and still 12 on the inside if you haven't opened your mouth wide. So the eardrum is bowed in like this. Well, again, it's tight and you can't hear well because it can't vibrate very well. But if you open your mouth wide, it snaps back into position. You hear what you call your ears popping, which is really the eardrum snapping back into position. And then you hear better. Okay, now there's one other thing I want to tell you. You can do a simple but dramatic experiment to demonstrate air pressure. If you're going to drive up to a high altitude like Sunrise or Paradise, anywhere that's 5,000 feet or more, get a very flexible water bottle like this one. You don't want a real hard plastic bottle like those little ones. You want a flexible one like this. Okay. Now, right now, the pressure inside and outside should be 14 because we're near sea level. Okay, you put the cap on and screw it on tight, and then you take it up with you to Paradise, and when you get up there, the pressure is going to be 12 on the outside but 14 on the inside. Who can tell me how the bottle will look? How will the bottle look when you get up there? How?
It'll be kind of like collapsed.
No, it won't be collapsed.
oh, it will.
It'll be bulged out because it's 12 on the outside and 14 on the inside. If you loosen the cap, you'll hear a rushing sound, which is the air equalizing to 12. So then, if you take the cap off up there, it becomes 12 on the outside and 12 on the inside. Put the cap on tightly, drive back down here. When you get back down here, now it's 14 on the outside and 12 on the inside. How's the bottle going to look, Stevie, when you get back down here? It'll be collapsed, partly collapsed.